And the Earth's crust seems solid, but what if it moves? This idea, seemingly simple, once challenged all geological understanding. Both the theory of continental drift began with a keen eye for shapes. A pioneering meteorologist, an individual named Wegener, proposed this radical shift. He observed fossil evidence suggesting warm climates in polar regions. Identical plant and animal fossils spanned oceans, defying known dispersal methods. Mountain chains appeared to abruptly stop, only to restart across the sea. Wegener named the ancient supercontinent Pangea, meaning all lands. A bomb but proposing movement required a mechanism, and that was the critical failing. His suggested driving forces, centrifugal force and tidal friction, were far too weak. The established view held that the Earth's crust was rigid and static. Despite compelling evidence, the scientific community dismissed Wegener's hypothesis entirely. He passed away without seeing his revolutionary concept accepted by his peers. Now that we understand the initial resistance, let's explore the hidden clues. Decades later, new mapping technology revealed unexpected features beneath the waves. But these vast underwater mountain chains were previously unknown to science. Crucially, rocks near these ridges showed symmetrical magnetic signatures. But this pattern suggested new oceanic crust was being continuously generated and spread. But this process, seafloor spreading, provided the missing engine for Wegener's drift. But if new crust forms, old crust must disappear somewhere else. This recycling occurs at subduction zones, where one plate sinks beneath another. These zones are the source of tremendous geological activity and intense pressure. Driving this monumental engine are massive convection currents deep within the mantle. But these currents drag, push, and pull the overlying tectonic plates along with them. But Wegener's intuition was correct that the continents were indeed drifting across the globe. The synthesis of these findings finally formed the theory of plate tectonics. Plate boundaries are where most of Earth's dynamic action occurs. Divergent boundaries create new crust, like the spreading Atlantic Ocean floor. This process constantly renews the ocean basins from below the waves. A continental rifting occurs when plates pull apart on land masses. Convergent boundaries, conversely, build the planet's highest elevations. Past subduction often leads to chains of explosive volcanic activity along the edges. Untransformed boundaries slide past each other horizontally, causing significant shear stress. A modern GPS technology tracks these movements down to mere centimeters per year. The acceptance of plate tectonics validated a legacy long ignored by the scientific establishment. Wegener's arc was one of foresight, requiring future generations to build the mechanism. When the entire lithosphere is broken into about a dozen major, rigid plates. And these plates interact constantly, dictating the planet's surface geography. Even the oldest continental crust drifts, albeit much slower than the oceanic crust. The magnetic tape recording confirms the constant creation and destruction of surface area. Mantle plumes, stationary hotspots, create chains of volcanoes far from plate boundaries. This explains the alignment of island arcs far from active convergence zones. The deepest parts of the ocean are trenches formed by relentless plate consumption. And the immense friction and resulting heat drive metamorphism deep within the crust. Understanding drift allows us to reconstruct Earth's past supercontinent cycles. This framework explains the distribution of life across separated land masses. But even river systems and drainage patterns are products of slow continental relocation. Seismology provides the final, indispensable confirmation of plate boundaries. The deep zones where earthquakes occur map the precise path of descent. Plate tectonics is the unifying theory connecting geology, chemistry, and physics. It explains how the dynamic Earth constantly remakes its own surface features. The story of continental drift is a lesson in scientific perseverance and open-mindedness. The initial rejection faded as the weight of evidence became simply too great to ignore. And the acceptance took nearly 50 years after the first radical proposition. Today, every oceanographic mission builds upon this foundational understanding of movement. The magnetic polarity embedded in rocks remains the most elegant proof. It demonstrates how new technology can validate old, dismissed observations. The Earth is not a static sphere, but a constantly reshaping, dynamic system. And we now see our planet as a vast, slow-motion jigsaw puzzle in motion. The story of drift reminds us that even the greatest ideas sometimes need time to move.